Okay, so after introducing ourselves or reintroducing ourselves into the general structure of waves and how they work and how to define them, we also introduced ourselves to the wave equation, the relationship between speed of a wave, the wavelength of a wave, and its frequency. After doing that, now we can get into some of the fun stuff, the characteristics of waves and all the interesting properties that they have, okay? So today, what I wanted to do, this isn't really in your textbook, but what I wanted to do is talk about a very important thing where we look at how we can calculate the speed of waves in different media. And the reason I'm doing that is because there's a lot of good potential IAs in this unit, and you don't necessarily have to do an experiment. You can actually make a math model and do everything on a computer simulation to look at things. So I just wanted to point out a few different ways of calculating the speed of a wave in a medium and looking at how that change in that speed affects characteristics such as wavelength of the wave. Okay, so the only thing that affects the speed of a wave is the medium. All right, now for mechanical waves, waves that travel through a physical medium, absolutely the density, how well the particles bind together and interact. We have a different type of wave, electromagnetic waves, that don't require a medium. So that's kind of strange. It says that the speed of a wave is affected by the medium. Well, electromagnetic waves don't require a medium, but media definitely affect the speed of electromagnetic waves, and we'll learn about that at the end. Okay, so let's start with what we learned to begin with and analyzing the speed of waves in a string. So with the SL class, we did a little simulation on PhET, where we were looking at making waves and strings and exploring what are the variables that affect the wavelength and the speed of that wave. And what we found out is that the speed of the wave in a string is related to the tension, how tight that rope is, and how heavy, the mass per unit length of that string, okay? So if we looked at that, this is the actual mathematical formula. So if we did an experiment and played around with the graphs, we would find out that the speed of that wave is proportional to the square root of the tension and inversely proportional to the mass of the string per unit length. Okay, so that's a characteristic. You take the total mass of that string and divide it by the length of the string, and that gives you how many kilograms per meter is that string. Okay, and that'll affect the speed. You can imagine the heavier it is, the harder it's going to be to propagate energy through it, the more kinetic energy it's going to take to move it, and that's going to affect velocity dramatically. Okay, so the square root probably comes from the kinetic energy formula as well. Okay, so here's a question that says the kid in the picture above vibrates a 6-meter rope that has a mass of 2 kilograms with a frequency of 5 hertz. The result of this vibration is the wave pattern shown in the picture. Use this information to calculate the tension in the rope. So they want to find the tension. Okay, and notice it said vibrate. So the kid is vibrating vertically up and down. He's making a transverse wave. Okay, and this wave is going to be reflecting off of the rope coming back the other way. All right, and I have to use all this information to solve for the tension. So you can pause it and try to solve it on your own. And if you don't pause it, here we go. Okay, so the first thing I need to do is start figuring out my variables. All right, I don't have the speed. Okay, so we don't have the speed, so we have to try to find the speed. What we're trying to find is the tension. Okay, so I'm going to put a box around that. So I'm trying to find the force of tension, but another variable that I don't have is the speed. So I'm going to have to try to find the speed of that wave in the rope before I can even get to the tension. We definitely have mass over unit length because they gave me the mass of the rope, 2 kilograms, and they gave me the length of the rope, which is 6 meters. So that variable has been given to us, okay? So how are we going to go about solving for velocity? Let's start with that. So I'm going to go back to an equation that we've already seen before, okay, where velocity is equal to the wavelength times the frequency. Okay, they've given me the frequency, all right? So how do I find the wavelength? All right, so I'm going to change the color here. This is a 6-meter rope, okay? And how many wavelengths are already inside of that 6-meter rope? So here is a wavelength, here's a wavelength, and here's a wavelength. So there's 3 wavelengths. Okay, so then I know that my wavelength is 2 meters. The mass per unit length is going to be 2 kilograms divided by 6 meters. Okay, my frequency is 5 hertz. Those are all the variables that I know. Okay, so I can solve for the velocity now. Velocity is equal to a 2-meter wavelength times 5 hertz, which is going to be equal to 10 meters per second. That's pretty convenient. And now that I have that, I can go back to the original equation to solve for the tension. So before I'm going to plug numbers in, I want to rearrange that original equation. Okay, so V squared is equal to Ft m over L. Okay, so then V squared times m over L, okay, I'm just going to show that I'm moving over here, is equal to Ft. So then 10 meters per second squared times, I'd say that's 1/3, because 2 kilograms over 6 meters is going to be 1/3, okay, is going to be equal to Ft. So 100 times 1/3, 33.3 newtons is equal to the force of tension, I believe. I could be wrong, but I believe that's the case, okay? So that's just an example. So for at a tension of 33.3 newtons, that string is going to have a velocity of 10 meters per second, and all those variables are put together to solve the problem, okay? So you can see that in order to solve this problem, I had to use 2 different equations. I have to be very comfortable with this equation to solve for a variable, okay? So using the information in a graph, using an equation that wasn't given to me, and then to use those 2 pieces of information together to then find something that I can then plug into another equation that's very, very IB and very, very higher, not higher level, but standard high school and university level physics, okay? So the next thing, now this isn't in our curriculum, but a lot of kids like to do this for an IA, and even last year for our Group 4 project, we went to the ocean and some kids analyzed the physics of waves in water, okay? And as I said in the last video, water waves are very complicated. They're not transverse waves, they're not longitudinal waves, they're a special type of wave called a rolling wave, okay? And they're quite complicated because they have a little bit of both characteristics. So that's beyond the scope of our curriculum, but this idea about doing an experiment with water waves is very easy, because you can research, and that's what I did. I researched an equation for the speed of the wave, and what I found out was that the speed of a water wave changes, and it depends on the depth of the wave, okay? So if we're in the deep part of the ocean, and that depth is greater than half of the wavelength of the wave, that wave is going to travel according to this relationship, where the speed is going to be equal to the square root of the acceleration of gravity times the wavelength of that wave divided by 2 pi square root. So nowhere in there is the depth. It can be 100 meters, 200 meters, 300 meters. That speed is always going to be the same in the deep regions. However, when we get to the shallower regions closer to the shore, we see that the waves start to bunch together. Okay, they're very far apart and they're consistent, but when they get closer to shore, they start to bunch together. And that's because now the equation changes. The speed is equal to the square root of acceleration of gravity times the depth. And as the shore gets shallower, that speed is going to change. And what effect does that have? If I change my speed, okay, I'm going to be affecting my wavelength. And something that's really important, like I said in the last video, for waves, the frequency is always constant, because that's what caused it. The vibration, the frequency of vibration that caused the wave created the wave, and it's always going to be constant. Okay, so if my speed changes, frequency is constant, that means that the wavelength has to change as a result, and they are directly proportional. Okay, so if my speed goes down, my wavelength goes down. If my speed goes up, my wavelength goes up. Okay, I think that's true. Okay, yeah, you can see that the speed is slowing down, so the wavelength is getting shorter. So a common experiment that students do is to explore these mathematical relationships in something called a ripple tank, and you can do this at home. Okay, if you have a bucket of water, all right, that you can change the depth of the water in, all right, so then you can create, just by shaking the ripple tank, if you can shake it at a constant frequency, you will make waves, and you can film that, and hopefully you'll be able to see the ripples in the water tank. And then if you put a block underneath or something to change the depth within it, you should be able to see a change in the wavelength as the water is going over top of that block, okay, because the depth has changed. All right, so a common research question would be, how does a change in the depth of water affect the speed or wavelength of a water wave. You can probably go back to here and try to see if you can affect other things, okay, and do some research. Is it just the depth, or is there other things such as density? I'm not sure, okay? You'd have to do some research for that, okay? So very common IA. So how would you go about designing an experiment at home to get done during this time while you're sitting at home, to use the wave equations to create an IA around that research question? Okay, you have to make a math model in your background information. Your math model is used to make a hypothesis, okay, and then that hypothesis will help you with the variables that you're going to set, and then off you go, and maybe you can easily do an SLIA already, okay? Another one, just to talk about, is kids like to analyze the speed of a wave in different media if they're talking about musical instruments, okay? So in liquids, all right, here's an equation that describes the speed of a wave in a liquid, where here, look at that. It depends on the density of the liquid. So if I change the density of the liquid, I'm going to affect the speed. So if I added salt to water, I wonder how that would affect the speed. Okay, and the bulk modulus, you'll have to check out and do some research what that variable is if you wanted to do an experiment where you're changing a variable in a liquid and looking at how it affects wavelength. All right. On the other hand, if you wanted to look at solids, like a xylophone, you're making a musical instrument. I know that Nate wanted to do that for his extended essay. Okay, here's how it relates. If I change the density of the solid, it's going to affect the speed of the wave, which is going to affect the frequency or the wavelength that material makes. And the Young modulus depends on how well something stretches and bends. So different materials have different Young's modulus, okay, and you can go and research what that is. Now in a gas, this is really interesting. With a gas, the speed of the wave depends on temperature. See, pressure is here. So temperature definitely affects how fast sound moves in air, and density of a gas. Okay, so speed in a gas is much slower than the speed in a solid and a liquid. And you can also research why. Okay, so that's a good question to look in. Why would the speed of a wave in a gas always be slower than these other media? Okay, and remember, like, the speed of, what I mean by that is a speed of a sound wave or a mechanical wave, all right? That you can do some research into those formulas, all right? So the last thing I want to talk about is electromagnetic waves, where electromagnetic waves don't require a medium. So this whole talk is about how the medium affects speed of waves. But as we said and introduced in the last video, electromagnetic waves travel in outer space, okay? It's made by an oscillating electric and magnetic field. So why would a medium affect a field? Okay, well, it affects how well that field can propagate through it. Okay, so the fastest medium for an electromagnetic wave to travel through is a vacuum, where there's no particles in it, nothing for it to interact with. And at that place, it's going to travel at a speed of 3 times 10 to the 8 meters per second, which is the speed of light. Okay, in a vacuum. But as soon as I start traveling through a material like a gas or a liquid or a solid, you can see that that speed of light no longer is 3 times 10 to the 8 meters per second. It starts to slow down, okay? In air, it still is 3 times 10 to the 8 meters per second. But once it gets into water, you can divide that number by 1.3. That's how much it gets slowed down. And in a solid, in diamond, you can divide that number by 2.5. It gets slowed down by a lot. So how do I know these things? Okay, well, there's an equation for that, and we use it often when we'll talk about refraction. But the equation is right here. Okay, the speed of light, okay, or a speed of an electromagnetic wave, depends on the dielectric constant of a medium. Okay, and the dielectric constant is a measure of how polar, okay, the polarizability, how many electrons can polarize. Like if a medium is filled with particles that have electrons, okay, that medium can become polarized and it'll interact with electric fields. Every particle will shake hands with a light wave and cause it to slow down. Okay, that's another way you can take a look at it. All right, so the greater the density of the material and the greater the electrons and polarizability of the material, the greater the dielectric constant of the material. Okay, so you can do some research on that if you're interested in this. Okay, and then definitely solids like diamond, which are really dense, are going to slow down the speed of light by a lot. Okay, and it's going to change the wavelength of light that is inside of that material. Okay, And that's that. So I just wanted to present this to you. It's not in your textbook, okay? But these are very, 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 very important and very useful relationships if you want to be able to design a really cool, simple IA to start looking at, okay? And I encourage at least two of you guys to look into designing an IA on musical instruments or light traveling through a medium. They're very, very straightforward.